All right, I've pulled this picture from our textbook. It is a picture of a prism, so a triangular prism here. This is made of glass, and the prism is surrounded by air. So air is outside everywhere. Glass in here is the prism itself. So we have an incident light ray. Incident ray means the light that's incoming. So there's some sort of laser over here shining light in this direction. When that laser light hits this first surface, when the light hits this surface, if you recall the law of reflection, we say this incoming or incident angle has to equal the reflected angle. So we get some of the light that is reflected, even if we don't want it per se. Just the fact that there is a boundary there, a surface, some of that light gets reflected off. But notice, some of the light is not reflected. As it says right here, this is light that is refracted. So we're going to be talking about refraction. Notice this incident angle I drew. Again, we measure these angles relative to the normal line. So the dotted line I drew represents the normal line. So it makes a 90-degree angle with the surface. Theta incident is measured relative to that normal line. Over here in the glass, if we measure from the normal line to the light ray, we call this the refracted angle. Notice that refracted angle, I'm going to call it theta sub r. In this particular case, this refracted angle is smaller than that incident angle. And if we pulled out a protractor, we could measure a difference in that angle. And the reason why is because of this concept called refraction. If you recall, the speed of light changes as it enters a new medium, a new material. N here is called the index of refraction of the material. So for vacuum, the absence of anything, N is exactly 1. We could write it as 1.0000. Air, index of refraction. I'll grab my test notes, make sure I give you the right number. Air, 1.0003. Index of refraction is a number without any units. It's just the amount of, or I guess the factor by which the speed of light will slow down. Water, for example, N is 1.33. So if we think about the speed of light that enters water, it slows down by a factor of 1.33. Because it slows down, it also changes direction. Kind of a silly example, but have you ever been in the grocery store and you have the shopping cart and you're pushing along, you're moving, and then one of the wheels gets stuck on something? If I had been looking down on the cart and we were moving this way, and this is the wheel that got stuck, the cart turns and starts going that direction. And that's because this left wheel keeps going at the rate I was pushing it, but the right wheel gets slowed down. So if the left side's traveling faster than the right side, then there is a change in direction. Kind of a silly analogy, but in general, light, because it is slowing down as it enters this glass, it ends up changing direction. So when light slows down in a new medium, the refracted angle is smaller than the incident angle. That's what we see in this picture. The incident light ray was in air, index of refraction of essentially 1, but then the light that continues into the glass slows down because we're now into glass, which is going to have an index of refraction that is greater than 1. In fact, it's probably close to 1.5. It depends upon what type of glass this is. So we see this refracted angle get smaller. Now notice at this other surface on the right, that green's kind of hard to see, we have another surface here. If I draw a dotted line representing the normal, so perpendicular to the surface, our incident angle now, theta incident 2, is smaller than theta refracted 2. As the light ray goes back out into the air, that angle gets bigger. And that's because the light speeds up. So in the glass, the light is traveling slower. As it enters back into air, it's traveling faster again. And because it's traveling faster again, this angle is bigger. So essentially, when light speeds up in a new medium, because it was in glass, it is now in air, the refracted angle is greater than the incident angle. Now, if instead of a laser, if this had been just white light, we would see a rainbow on this side, on the right side, as it came out of this glass, because this is essentially a prism. The reason why we would see a rainbow is that these indices of refraction, like for water, this 1.33 is an average. It technically is slightly different for each wavelength of light, which means each wavelength of light has a slightly different amount of refraction or bending that occurs. And that's why we would see a rainbow. Here, laser light, we only see that one beam. We are not going to take into consideration the difference of these indices of refraction based on wavelength. I did want to mention it though, because I imagine you've probably seen a rainbow after the light has passed through a prism. Okay, so refraction occurs because the speed of this light wave changes as it enters into a new medium. On a side note, the frequency stays the same in each medium. So if you remember back to waves in general, the speed of a wave is wavelength times frequency. If frequency is staying the same, but speed changes, then wavelength must change as well. So we can say that the wavelength of light in a new medium follows the similar relationship that the speed of light does. All right, so we have an equation that describes and relates our incident angles and refracted angles. So with refraction, Snell's law is the equation that relates the incident angle to the refracted angle. This equation looks like this. N1, meaning the index of refraction in the first medium that the light is in, times sine of theta 1. Theta 1 being the angle in the first medium. That has to equal N2 sine theta 2. This equation is valid at one surface at a time. So what I mean by that, if I look back up to our picture, we can use this equation on this left-hand surface. So at this surface, what we would mean, is N of air, because that's where this incident light ray is. Theta 1 would be the angle of the light in the air measured from the normal line. So the normal line, remember, is perpendicular to the surface. So essentially, if I redraw that surface, this light ray that's coming in, so this was our incident angle, I would draw my normal line. Theta 1 would be this angle that the light makes relative to the normal. N1 is 1 for air. The light, though, is coming into the glass, and we see that that angle, this would be our theta 2, that angle got smaller because N2 is whatever glass is, and that's going to be bigger than 1. So if we were to set up our equation, we would say N in the air, so the index of refraction of the air, times the sine of this theta 1 right here, the angle measured relative to the normal, I'm trying to star that, would equal N of the glass, so we're now in this new medium, times the sine of theta 2, which is this angle that the light ray makes relative to the normal again. But theta 2 is less than theta 1 because N of the glass is greater than N of air. So this is explaining what I mentioned here. When light slows down, the angle gets smaller. Well, the light slows down because the index of refraction is larger. With a larger index of refraction, we get a smaller angle. Okay? So Snell's law, this equation can be used only at one surface at a time. So one boundary between two different materials. If light is going from a higher index of refraction to a lower one, for example, that second surface of the prism, it was angled this way, the incoming light was coming roughly horizontally. If I draw my perpendicular line, this theta 1 is smaller than this theta 2 because this was the glass of that prism and the light was coming back into air. So we would say N of the glass, that's where the light is located, sine of theta 1 is equal N of the air, because that's where the light is going to, times the sine of theta 2. Since N of the air is smaller, theta 2 is bigger. So refraction is dealing with the bending, the changing in direction that the light is traveling in because of that different medium. If you recall, well, not recall per se, if you've ever been in a swimming pool and you look down, if you're just standing in the swimming pool, your legs look shorter than normal. That's because as the light is coming in, here's our angle. Well, it's in air to begin with. It's going into water. Water has a higher index of refraction. Therefore, the light bends, and this theta 2 is smaller. So the light actually reaches the bottom faster than we would expect if it had been moving in a straight line. And ultimately, that's what makes our legs appear shorter because of that. So we're going to be talking about refraction. We'll talk about images we see because of refraction. And then we'll talk about thin lenses as well, and what, like glasses that you might wear. So I'll talk about that in a future video.